I'm going to discuss Heisenberg's uncertainty principle, but not through mathematical proofs like he gave to us. But we will just deal with as per layman's language, and I will make you understand how the principle works on the subparticle basis. Okay, let's start. But before starting, I should say you that in quantum mechanics, two things can be interchanged. The size of a subatomic particle can be changed with the position of the subatomic particle. That is, they are just interchange. They can be interchanged. They are same. In actual sense, they are same as the quantum mechanics. Now let's get started. What I am going to tell you. I take a particle here, and I have to measure the position and the position of the particle, or I have to measure the length of the particle or the size of the particle at a definite time, at a definite interval of time, in a definite amount of space. Okay. So for this reason, what I should do, I will take a wave. Just to locate or just to measure the size or just to measure the size of the particle, I took a wave and throw it at the particle. Now when I throw it at the particle just will take some amount of space of the wave. Just let us assume it gets settled at here. And we know take the wavelength of the wave as z nanometer. So when I took the particle and it settled here in the trough of one of the troughs of the particle, and the trough distance, just let the trough length is z nanometer. So basically what I can say is simply I can say the size of the particle is less than z nanometer. Now you can say me how? Because it just settled here, it occupied some of the space of this trough but left much more behind. Here it is here. So obviously the space occupied by the particle will be less than z nanometer, because the space it occupied is much more less than it has to be occupied, because if we will say that it has to occupy the z space of the wave, then what we have to do, it should occupy whole space here. But it is not occupying the whole space, it is occupying little space here. So we can say that the size of the particle is z nanometer, okay, less than z nanometer. But now the question arises, well, less than z nanometer, but what is the size of the particle? Yes, we know it is less than z nanometer, but what is the actual size of the particle? That is what I can say. I'm just saying maybe it is z minus a, z minus b, z minus c, something it is, but I don't know that. So what it actually means is this uncertainty in its position or in its size. We are just unable to measure its size too correctly when we use the wavelength z nanometer. So simply it is this. Now what I will do, I will take another wave. When I took another wave here and I put it on the particle, subatomic particle, it occupied the trough. Fully it occupied the trough. This time I'm sure, because it fully occupied the trough, this time I'm sure its size is equal to z nanometer, and there is no objection in it. It is an universal truth here, because it occupied full volume, it occupied full space here, it occupied full space. So I can say let the wavelength of the wave be z nanometer here too, and I just put it onto the particle, and the particle just occupied full space of the trough. When it occupied full space of the trough, I can say, oh yeah, here what it is, z size of the particle is z nanometer, because it left no space behind. It just settled in a z length. Okay, when it settled into a length of z, so we can say its length is also z nanometer. It is so simple. But now the question arises here. When I just put it, when I put the wavelength z nanometers, let us assume here it is x nanometer. So here it has much more less wavelength than this wave has much more wavelength than this wave. So here it was z nanometer. Let's assume here is x nanometer. Okay, so its size is now x nanometer. The particle size is x nanometer. But now what is the problem? I just took a wave which has much more wavelength, which is lambda equals to z nanometer. But here lambda was x nanometer, and from this we can say that lambda 1 is greater than lambda 2. It is much more greater than it. But we can also say that we know that wavelength is inversely proportional to the frequency. We can say that 1 by V1 is greater than 1 by V2. What it means is, if what it means is that the frequency of the first wave is much more less than frequency of the second wave. So when the frequency of the first wave is much more less than frequency of the second wave, it means that the energy of the first wave is much more less than the energy of the second wave. So this wave has much more less energy than this wave. Much more. So when we take this wave, and it has much more less, it has negligible energy. We can assume it has negligible energy. And when this wave just strikes the particle, this energy gets added to the kinetic energy of the particle. When the energy gets added to the kinetic energy of the particle, it helps the kinetic energy of the particle increases. But due to the negligible amount of energy into the wave, it does not get added to the kinetic energy. So there just the kinetic energy of the particle remains unaffected. So now the kinetic energy of the particle remains unaffected. When the kinetic energy of the particle remains unaffected, that means there will be no increase or decrease in the space. There will be no increase or decrease in the speed. The particle will travel with the same speed it was traveling before the wave fall on it. Okay. So from this we can say that it was uncertainty. We were unable to calculate the position of the particle, but we can say that what was the speed? That was same. The speed before we just the wave struck on the particle is same after the waves struck the particle, because it has much more less energy that it does not get added to the kinetic energy of the particle. So when it not gets added to the kinetic energy of the particle, the speed of the particle remains the same. But when we use this wavelength, this wave of wavelength z nanometer, we were unable to measure the position. But the speed remained unaffected, so we can accurately measure the speed of the particle. But the position of the particle we will be unable. If we will be able to, it will be very uncertain. There will be uncertainty into it. But in case of this, the frequency of this wave is much more than this wave, and thus the energy is also much more greater than this wave. So okay, when it has an energy, sufficient energy, so this energy gets added to the kinetic energy of this particle. So when this energy gets added to the kinetic energy of the particle speeds up. When the particle speeds up, we got the precise, and we got the certain position of the particle. But when now we are going to check the speed at that point, but we know that the energy of the wave got added to it, so there will be uncertainty into it, because when the energy of the wave got added to the kinetic energy of the particle speeded up very much. When particle speeded up, now but we calculated the position with a good certainty, but the speed got up and we were unable to calculate it. So at a single time we can just calculate only one thing with certainty, and in other thing there will be 100% uncertainty. And that uncertainty is greater or equal to h divided by 4 pi. Thanks.